Hello everyone, I am Juhan from Seoul National University. I am very happy to introduce our work Heimdall, which is a mobile GPU coordination platform for emerging AR applications. This work was done in collaboration with my advisor, Professor Young-Ki Lee. Imagine an AR application scenario where a user is shopping a couch in an online store. He wears an AR glass and sees the list of couches available. When he selects the one he likes, the AR glass displays it in his room in an adequate position relative to other furniture. He can also move his hands to adjust the location of the couch, and he can also transform the texture and the color of the couch to determine which one best fits in his home. To support such future AR apps, what do we need? First, we need to continuously and concurrently run multiple DNNs to analyze the physical world and user behaviors, as well as create virtual contents. For example, in the above scenario, we need to run object detection and segmentation to find the locations of the furniture, hand tracking to track the user's hand movements, and image style transfer to change the color and texture of the couch. Second, we need to run rendering tasks to seamlessly overlay the virtual content, the couch in this case, over the physical world. Finally, all such tasks need to run on resource-constrained AR glasses, preferably on the GPU for lower latency. So summarizing, future AR apps require a concurrent execution of multi-DNN and rendering tasks on resource-constrained mobile GPUs. Now, the above example is not just one special case. We observed that such workload is a very common requirement across multiple application scenarios. For example, we can think of a police officer chasing a criminal with the help of the AR glass running the face identification algorithm, or an interactive workspace application where the user overlays the virtual documents over the physical ones and freely interacts between them. All these applications require concurrent multi-DNN and rendering tasks across on resource-constrained mobile GPUs. Recently, there have been many deep learning frameworks released for mobile devices. However, we find that they are ill-suited for future AR applications mainly because of two reasons. First, they are designed to run only a single DNN and cannot support a coordinated execution between multiple DNNs. Second, they are designed to run a DNN in an isolated environment where no other task is contending over the mobile GPU, and thus cannot support flexible coordination with rendering. We have actually measured what happens when running the concurrent multi-DNN and rendering task using existing mobile deep learning frameworks. Here we present the results using Xiaomi Mei's framework over LG V50 smartphone, but the results are common across other frameworks and devices as well. First, let's see how the DNN inference latencies are affected when running the 4 DNNs required for the above shopping scenario. The x-axis shows how many DNNs are concurrently running, and each bar denotes the inference times, where the error bar denotes the standard deviation. Style transfer stands for the style transfer model. YOLO v2, Deep Lab, and PostNet stands for object detection, image segmentation, and hand tracking, respectively. First, we see that when we run all the DNNs separately, the total inference time is about 500 milliseconds, meaning that they can run at roughly 2 frames per second, which can be enough in designing the above application. However, as more number of DNNs run concurrently, the contention overhead occurs and increases the inference latency. How much the inference latency increases depends on the DNN model. For example, the style transfer model's inference latency increases from 16 milliseconds to more than 1 second. We will analyze this behavior in depth very shortly. So summarizing, multi-DNN GPU contention degrades inference speed. We also see that when rendering is running with multi-DNN tasks, the frame rate also drops. For example, with the same setting as before, compared to the case of stable 30 frames per second when camera is running alone without any DNNs, the frame rate drops with more DNNs running in the background. More importantly, when we see the frame rate over time, we can see that it actually fluctuates heavily, which significantly degrades the user experience. So rendering DNN GPU contention degrades the frame rate and user experience. Why is the above GPU contention happening? The reason is because mobile GPUs are FIFO. Let's take a closer look on what it means using an example of what happens when 3 DNNs are running in parallel. Using the commercial mobile deep learning frameworks, the only way to support multi-DNN execution is to launch multiple inference engines on different threads and run them in parallel without any coordination. So before executing the model inference, we need to do some pre-processing steps such as resizing the images. This depends on the model, and let's assume that DNN2 is first in queue to the GPU. When DNN1 and 3 finish their pre-processing and tries to access the GPU, the first contention occurs as DNN2 is already occupying the GPU. So DNN1 can only start when DNN2 finishes. While DNN1 is running, let's assume that some layers or operators in the models are unsupported by the GPU backend of the framework and needs to fall back to the CPU. This actually happens quite frequently. For example, in TensorFlow Lite, the max operator falls back to the CPU. In such a case, DNN3 takes over the GPU. Another contention occurs when DNN1 finishes the CPU fallback executions and comes back. It cannot access the GPU right away again because DNN3 is already running. As a result, DNN1's inference time is delayed significantly. And actually from this, we can see that the inference latency will actually increase more when there are more number of competing DNNs and more number of CPU fallback points in the model. This explains why the style transfer model in the previous slide suffers from the most contention. It is because it has several fallback points compared to other competing models. Some of you may think FIFO scheduling is very naive, and why don't we apply more intelligent scheduling techniques? In fact, they are available in desktop GPUs. However, they are very challenging to employ in mobile GPUs. One possible approach that we can consider is partitioning the GPU computing resources and running multiple DNNs in parallel. However, this kind of approach requires the underlying architecture support, but are unfortunately not supported in mobile GPUs. Another approach that we can think of is the preemptive scheduling, where we can set the priority between multiple DNNs, and the high priority DNN1 can interrupt the already running DNN2 and gain the access to the GPU immediately. This is also possible, but the main drawback here is that to interrupt the task, we need to trigger a context switch, which involves saving the intermediate memory states. Unfortunately, this is challenging for mobile GPUs, as not only the memory bandwidth itself is limited, but it is also shared with the CPU due to a mobile system on-chip design. To tackle the challenge, we designed Heimdall, the first mobile GPU coordination platform for AR applications. To coordinate concurrent GPU tasks, we designed a pseudo-preemption mechanism, which mimics the effect of preemption without any memory overhead. How do we do that? The trick here is determining when to trigger the context switches. Conventional preemption triggers context switches regardless of the app context, which incurs a large memory overhead to save the intermediate GPU memory states. However, our pseudo-preemption triggers context switches only when a semantic unit of a task is finished and the result must be saved. This actually incurs no additional memory costs. So the key in enabling our pseudo-preemption mechanism is dividing the task into smaller semantic units and triggering context switches only at those checkpoints. Here the question arises, how fine should we divide the task, and is such fine partitioning even feasible? First, we see that for the rendering task, the latencies are already typically very small. For example, 2.7 milliseconds for a full HD camera frame, meaning that rendering tasks do not need to be divided anymore for fine-grained time sharing. In case of DNNs, however, we see that the model inference latency is often too bulky and cannot enable fine-grained time sharing. However, we observe that the DNNs are actually a sequence of operators, and when measured in the operator level, the latency is typically very small. In fact, The CDF of the operator latency in the state-of-the-art DNNs show that about 90% of the operators run within 5 milliseconds, which means that the DNNs can be divided into the units of operators for fine-grained time sharing. So Heimdall incorporates two components to realize the pseudo-preemption mechanism, namely the Preemption-Enabling DNN Analyzer that breaks down the bulky DNNs into smaller units, and Pseudo-Preemptive GPU Coordinator that schedules concurrent GPU tasks. So first, the Preemption-Enabling DNN Analyzer breaks down this DNN into smaller units. The question in designing the analyzer are twofold. First, when should we divide the DNNs? Actually, we found that offline profiling and partitioning is feasible, as mobile GPUs do not support preemption, meaning that the profile task latency at offline stage will be the same at the online runtime. Second, how should we divide the DNNs? We mentioned earlier that the DNNs can be divided into the units of operators, but when we divide them too finely, the inference latency overhead can be significant. For example, dividing the DNNs by single operators incurs as high as 70% latency overhead. Therefore, the analyzer optimizes the partition size by packing as many operators as possible between rendering events. For example, assuming that the target frame rate is f/fps and each rendering latency is tr milliseconds, the DNNs will have 1 over f minus tr milliseconds to occupy the GPU between the rendering events. Accordingly, given the DNN model, which is a sequence of operators, the analyzer determines the partition indexes pi so that each partition execution latency falls within the available time and actually remains as close as to the available margin. So the Preemption-Enabling DNN Analyzer breaks down the DNN into chunks, enabling the pseudo-preemption mechanism. The Pseudo-Preemptive GPU Coordinator utilizes this mechanism to flexibly coordinate multiple DNNs and rendering at runtime. Our design philosophy is that, given the rendering and DNN task, we give the highest priority to the rendering task and run it at the target frame rate, as rendering directly affects user experience. And between the rendering events, we utilize the priority-based scheduling technique to coordinate multiple DNNs. To schedule multiple DNNs, we actually need a formal way to compare which DNN is more important to run at a given time. For this purpose, we design a utility function for each DNN. Here, the utility function is a function that changes over time, and actually it can be designed in any way that fits the application's performance goal and can be incorporated in our system. So we designed one example utility function, which is composed of the latency utility, which measures the delay or freshness of the inference over time, and the content variation utility that captures the scene changes from the last inference. Please refer to our paper for more details. So given the DNNs and their utilities, the coordinator schedules their execution to maximize the overall performance at runtime, which is defined as a policy. So we have designed two policies. First, the max-min utility policy fairly allocates GPU resources among the DNNs. And second, the max total utility maximizes the overall utility sum by running the high priority DNNs more frequently. Again, there can be many policies that can be designed based on what the performance goal is, and they can be flexibly incorporated in our system. We evaluate the performance of our system using the following setup. We use the LG V50 smartphone as a computing device, and we use the OpenCL-based Xiaomi Maze framework. For comparison schemes, we use the baseline multi-threading approach, which runs multiple DNNs in multiple threads without any coordination, and also the modal agnostic partitioning scheme, where we enqueue only 5 DNN operators at a time, so that a single DNN does not occupy the GPU for too long. For the application scenario, we use the immersive online shopping scenario that we have seen before, with the following application requirements. So for rendering, we need to render full HD camera frames at 30 frames per second. For DNNs, the style transfer model should run with less than 0.1 second response time, and YOLO, DeepLab, and PostNet should run at 1 and 2 FPS respectively. Let's first see the GPU coordination performance of Heimdall compared with baselines. In terms of rendering frame rate, baseline suffers from low frame rate as well as heavy fluctuation. Model agnostic partitioning enhances the frame rate as it avoids DNNs from taking the GPU for too long, but it still suffers from fluctuation. On the other hand, Heimdall supports a robust 30 frames per second rendering frame rate. In terms of DNN inference latency, baseline solution shows a significant contention overhead. Model agnostic partitioning reduces the contention to a certain amount, but still fails to satisfy the application requirements, especially that of the style transfer model. On the other hand, Heimdall efficiently coordinates them to satisfy the goal, which is done by putting the higher priority to the style transfer model and running DeepLab model at minimum to satisfy the application requirements. In summary, Heimdall enhances rendering frame rate from 12 to 30 frames per second and reduces the worst case DNN inference latency by up to 15 times, which is the case for the style transfer model. Next, we show how the GPU is shared for different coordination policies. The top figure shows the utility of the 3 DNNs over time. For example, when the DNN inference is first enqueued, such as the PostNet model colored in blue line at the time t equals 200 milliseconds, the utility remains very high. However, as time passes, the utility drops as the inference delay increases. The bottom figure shows how the rendering and the DNN tasks occupy the GPU over time. We can see that rendering periodically occupies the GPUs, and under the max-min utility policy, the DNN with current lowest utility is executed, enabling fairness. Compared to that, under the max total utility policy, a DNN with a higher priority, which is the PostNet in this case, colored in blue, is more frequently needed than others. And as you can see that compared to the previous slide, the utility of PostNet remains much higher and occupies the GPU more frequently. Before we finish, we would like to discuss some questions that can be raised for our system. The first question that we want to discuss is whether our system is generalizable to other mobile deep learning frameworks. Our answer is yes, because Heimdall does not require any OS or underlying system supports. To extend Heimdall to other frameworks, it requires only marginal fixes to support the partial DNN inference. Another question we want to discuss is whether Heimdall can be used for emerging neural processors that are embedded in mobile devices, recent mobile devices, to accelerate the DNN inference. We expect that our pseudo-preemption mechanism will be used for such processors as well, as they are composed of a large number of hardwired matrix multiplication units, which are very hard to preempt due to possibly larger memory states than the GPU. Let me summarize our talk. In this paper, we presented Heimdall, a mobile GPU coordination platform for emerging AR applications. Our key idea is designing a pseudo-preemption mechanism to coordinate multiple DNNs and rendering tasks, which enhances the frame rate from 12 to 30 frames per second and reduces the worst-case DNN inference latency by up to 15 times. We expect that our system is generalizable across different frameworks and processors. Please contact us in case you have any questions. Thank you.